Right. Nope. It's very cold this morning. I'm not a fan. It's cold. We warm. Here's the attendance form for those of you on the Zoom. Almost time. It's almost time. This is time to get started. That's nice. All right. So just a couple things. Exam, hopefully it didn't go too terribly. Hopefully it went well, actually, not too terrible. Hopefully it went well. I'll try and get those graded as soon as I can. Shouldn't take too long. Hopefully by the end of the week, I'll probably grade them on Friday, even though it's a holiday. Okay, fine. And just everyone's like thinking about the rest of the quarter, right? We have 5 days of class left. Today, Wednesday, and then Monday, Wednesday, Friday of next week. And then finals are after that. So, right, we're rapidly approaching the end of the quarter. So just think about that as you were planning out the rest of your quarter and your other classes, really, is what I would say. Today, we're going to talk more about the unit circle and some trig identities and kind of how I really think about evaluating trig functions of these various angles that have reference angles with their special angles. But some people like to do a memorizing thing. So we'll talk about both ways. So here is our unit circle, thus named because it is a circle of radius 1. So this circle, all these points are exactly a length of 1 from the center, which is at the origin. And the idea is that we're going to draw any old triangle. Specifically, we're going to draw it in the first quadrant just to make it easier to figure out what's going on here. But we're going to draw an angle, sorry, a triangle. And we're going to drop a perpendicular right there. We're going to call that angle measured from the positive x-axis theta. I'm on it. A little bit here. And we're going to remember that the radius of this circle, also known as the hypotenuse of this triangle, has a length of 1. And we are going to say that this point here that the radius extends to on the circle is the point x comma y. Because we've literally just gone over x and up y. And now here's kind of the connection between the triangle stuff we've been talking about and the unit circle. And that's that if I look at this triangle, I can say, well, sine of theta is the opposite over the hypotenuse, which is just y over 1, which is just y. Similarly, cosine of theta is the adjacent over the hypotenuse, which is just x over 1, which is just x. And tangent of theta is the opposite over the adjacent, which is y over x, which doesn't simplify. We might as well also throw in the reciprocal trig functions because they're also real things. Cosecant of theta would be the reciprocal of sine, which is 1 over y. Secant of theta is the reciprocal of cosine, which is 1 over x. And cotangent of theta is the reciprocal of tangent, which is x over y. Now, what we can do with this is we can use our special triangles to kind of think about how they're going to orient on the unit circle in various quadrants. So we still, from last time, right, here's our special triangles. I mean, not last time, from a couple times ago, right? You've got your 45, 45, 90 special triangle, whose sides are 1, 1, and the square root of 2. And you've got your 30, 60, 90 triangle, whose sides are 2, 1, and the square root of 3. And so what we're going to think about doing here is in our unit circle, our first angle, which is pi over 6, which I'm going to do in red. Let's be consistent here. Yeah. So this angle here being pi over 6. We're going to think about this point would be by kind of taking this 30, 60, 90 triangle and dropping it down right here. So take a look for a second. We're not going to do this for everyone because it's hard to draw them all. The idea is right there is my 30, 60, 90 triangle where I'm going to go over, well, I'm not going to go over root 3 and up 1 because my hypotenuse is in the length of 2. My hypotenuse is the length of 1. So I'm actually going to take all these triangles and make them so that they're hypotenuse of a length of 2. So I'm going to divide everything here by 2. So the idea here is I'm going to go over root 3 over 2 and up 1/2 to get a point of root 3 over 2 comma 1/2. The idea here is that this is actually equal to exactly cosine of pi over 6 comma sine of pi over 6. The whole idea is that, let me back up just a little bit here. This point on the unit circle is equal to cosine of theta comma sine of theta. The x coordinate is the cosine of the angle. The y coordinate is the sine of the angle. And so we could, although I'm not going to, we could take this 30, 60, 90 triangle and see that it also lives right here. And in fact, well, I guess, I mean, why not? It lives right there. There's the 30, 60, 90 triangle. And it also lives right here. And it also lives over here. meaning that this length here is also root 3 over 2. This is 1/2. This is 1/2. This is 1/2. The only difference is that in this quadrant over here, the x values are negative because we've gone to the left instead of to the right. And in the third quadrant here, the x and the y values are both negative. So this coordinate here is going to be negative root 3 over 2, comma 1/2. And this coordinate down here in the third quadrant is going to be negative root 3 over 2, comma negative 1/2. And this coordinate over here in the fourth quadrant is going to be positive root 3 over 2, comma negative 1/2. And all of these angles are the angles that have pi over 6 or 30 degrees as their reference angle. So this angle, which we talked about last time, which I know it's been a little while, but this angle over here, right? This one here is theta equal to 5 pi over 6. And this one down here is theta equal to 7 pi over 6. This one over here is theta equal to 11 pi over 6. So for any angle whose reference angle is pi over 6, sine is always going to be some sort of 1/2, either positive 1/2 or negative 1/2. And cosine is going to be some sort of root 3 over 2, either positive root 3 over 2 or negative root 3. And that's always the cosine and sine value for pi over 6 or an angle whose reference angle is pi over 6. My personal preference is to memorize that piece of information. The pi over 6 goes with those two values, and then just determine whether it's positive or negative based on, let's see, what quadrant we are in. So in the first quadrant, all things are positive. In the second quadrant, sine is positive. In the third quadrant, tangent is positive. In the fourth quadrant, cosine is positive. And we remind ourselves that all students take calculus. Or whatever mnemonic device you prefer to use for that. So we're going to do the same thing for the rest of these special angles that occur in this unit circle. So the next one here is theta equal to pi over 4 radians or 45 degrees. I suppose I could write pi over 6 equal to 30 degrees here. And for 45 degrees, instead of doing 1 over root 2 for sine and 1 over root 2 for cosine, we're going to divide everything by root 2. So the hypotenuse still has a length of 1. And we're going to get 1 over root 2, comma 1 over root 2, or root 2 over 2. Root 2 over 2. So this point here is root 2 over 2, comma root 2 over 2. The thing I like to remember about 45 degrees or pi over 4 radians is that sine and cosine have the same value. That is kind of the thing that always rings in my head. Oh, 45 degrees, sine and cosine are the same. Great. And also tangent is going to be 1. Same sort of deal in the other 3 quadrants. The only thing that's going to change is the SIGN, the positive or negativeness of either sine or cosine. So in quadrant 2, well, if I'm going to the left, my x coordinate is going to be negative, so I'm going to get negative root 2 over 2, comma root 2 over 2. In the third quadrant, they're both negative. Both x is negative and y is negative. Or if you prefer, cosine is negative and sine is negative. And finally, in quadrant 4, the x coordinate's positive, the y coordinate's negative. And the angles are in quadrant 2, 3 pi over 4. In quadrant 3, 5 pi over 4. And in quadrant 4, 7 pi over 4. So I just want to say again, very strenuously here, that these coordinates are the actual cosine and sine values. Right? Cosine of pi over 4 is the square root of 2 over 2. And that is actually how far over we've gone. Sine of pi over 4 is root 2 over 2. That is actually how far up we've gone. So we've gone over and up that amount on the unit circle. There's something else I want to say there. Oh, I know what it was. One way, so I've definitely seen in the past students kind of get which one is which confused, like is sine first or is cosine first. The way I really like to remember it is it's alphabetical. X comes before Y, cosine comes before sine. It starts with the C, sine starts with an S. So that's one thing that works for me. You might find something else that works for you, but cosine is always the X coordinate, sine is always the Y coordinate. And then lastly, we have our third special angle, pi over 3 radians. It's purple. The green is not great. The purple is pretty great. Pi over 3 radians. Or in quadrant 2, it's going to be 2 pi over 3. Or in quadrant 3, it's going to be 4 pi over 3. Or in quadrant 5, in quadrant 4, it's going to be 5 pi over 3. And the angles, or so I should say, the values are just the pi over 6 values, but interchanged. Instead of root 3 over 2 comma 1/2, you're going to get the x value being 1/2 and the y value being root 3 over 2. Or sine of pi over 3 or 60 degrees is 1/2 and sine of 6, I said the wrong thing there. Let me say that again. Sine of 60 degrees or pi over 3 is root 3 over 2 and cosine of 60 degrees is 1/2. A couple things I think about in the first quadrant here, as the angles get bigger, the cosine x values get smaller and the sine y values get bigger as you go from 0 radians to pi over 2 radians. And then once again, the pattern holds. We're just getting the same values, but the different signs. So here you get negative 1/2 comma root 3 over 2. Down here you get negative 1/2 comma negative root 3 over 2. And over here you get positive 1/2 comma negative root 3 over 2. I suppose we should also fill in the rest of these angles here. This angle is 0 radians or 2 pi radians. Over here you have pi radians. And down here you have 3 pi over 2 radians. So here's our totally filled in unit circle. It's got all the things we care about. I suppose you might also write angles in degrees if you wanted to. I wouldn't recommend memorizing all of this because I'm not good at memorizing things. It's just not a skill I have particularly developed in my life, which is unfortunate. I would memorize what's going on in quadrant 1. Be like, okay, for pi over 6 radians, cosine is root 3 over 2, sine is 1/2. For pi over 4 radians, cosine and sine are both the same. For pi over 3 radians, cosine is 1/2, sine is root 3 over 2. And then I would extend that to saying, well, in any other quadrant, I'm just going to look for the reference angle and then determine whether it's positive or negative based on which quadrant I'm in. From in quadrant 2, sine's positive, cosine's negative, change is negative. In quadrant 3, change is positive, the other two are negative, and so on and so on. You can take a break. Let's ask questions so far or observations that you might have noticed. Okay, if you don't have questions, but you're welcome to ask questions. I know it's a lot of me talking, but asking you guys have questions. Yeah.
What was the inappropriate version of your AC?
That's for office hours. That's for me not being on video. You're welcome to come ask me in office hours anytime. It's not that inappropriate. It's just mildly inappropriate. So sometime in office hours, yes. Come see me. Oh, there's something else I don't want to say here though. Something I've noticed about this, and again, it only kind of works with these special angles, is that each subsequent reference angle, each subsequent angle with a certain reference angle is just the next value that doesn't reduce. Meaning for pi over 3, the next angle with that reference angle is 2 pi over 3. The next angle with that reference angle isn't 3 pi over 3 because 3 pi over 3 reduces to pi. It's 4 pi over 3. And then the next one after that is 5 pi over 3. It also works with the pi over 4. It's pi over 4. The next one would be 2 pi over 4, but that reduces. So pi over 2. The next one would be 3 pi over 4. The next one would be 4 pi over 4, but that reduces. The next one's 5 pi over 4, that doesn't reduce. 6 pi over 4 reduces to 3 pi over 2. 7 pi over 4 doesn't reduce. So it's always the ones that don't reduce. It even works for pi over 6. Pi over 6, 2 pi over 6 is pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. 5 pi over 6 is the next one that doesn't reduce. That's the next one that has the same reference angle. And then 6 pi over 6, 7 pi over 6 doesn't reduce. And then 8 pi over 6 is 4 pi over 3. 9 pi over 6 is 3 pi over 2. 10 pi over 6 is 5 pi over 3. And finally, 11 pi over 6 is the next one that doesn't reduce. So if you're looking for angles that have the same reference angle or which quadrant they're in, you can always find the next one by finding the next one that doesn't reduce. So if I was trying to figure out like what quadrant 11 pi over 6 was in, and I didn't remember, I'd be like, well, it's not pi over 6. And then the next one that doesn't reduce is 5 pi over 6 in quadrant 2. And then the next one that doesn't reduce is 7 pi over 6 in quadrant 3. So it's got to be the one that's in quadrant 4 because it's the fourth one that doesn't reduce. It's not like a very efficient way of doing it, but it's certainly a way that works, and it's a pattern that is nice. So one of the reasons we care about this unit circle is because most of the stuff we've been doing so far has been dealing with finding sine, cosine, tangent, etc., for angles that you can put into a right triangle. Even if it's something that's bigger than 90 degrees or pi over 2 radians, we can still kind of imagine drawing a right triangle over in that quadrant. But sometimes there are angles that really, really don't work. Like, for example, or I should say don't work in a triangle. For example, finding something like sine of pi over 3. So sine of pi over 3, where is that? In fact, I might even start with a different value first. What about cosine of pi? Well, this is why we are using the unit circle. So we look back at our unit circle for a second. We can see that pi is right here, and cosine of pi is going to be the x coordinates. So this definition that sine of theta is always the y coordinate and cosine of theta is always the x coordinate, tangent of theta is always y over x, is true for any angle on the unit circle, regardless if it's one we're familiar with or one that's kind of new to us. Even if it's one of these, what we call quadrantal angles, where we end up on one of the x or y axes. So pi over 2 or 90 degrees, pi, which is 180 degrees, 3 pi over 2 or 270 degrees, and 0 radians, which is 0 degrees, or 2 pi radians, which is 360 degrees, or any like further angle like 450 degrees or 6 pi or anything that ends up on one of those axes is called a quadrantal angle. It's kind of, I like saying the word quadrantal. It's just fun. Say quadrantal. I say it all the time. You wouldn't believe it. I just say it's like, oh, quadrantal. Anyway, the point is that if you end up on one of these quadrant barriers, which is why we call them quadrantal angles, you can still find sine or cosine by just looking at the x or y coordinate. That's kind of said this backwards. You can find cosine or sine by looking at the x or y coordinate. So cosine of pi is exactly -1, because that is the x coordinate at pi radians down here. Sorry, you can't see that at all. I keep moving things around. Pi radians, cosine -1. And in a similar way, sine of pi would be 0. And in a similar way, cosine of 3 pi would also be 0, because 3 pi is just, well, there's a whole revolution at 2 pi, and then going around halfway again, that's exactly an angle of 3 pi radians. That ends us back at the same spot there. That spot is where the y coordinate is 0, and the x coordinate is -1. So we can say that sine of 3 pi is equal to 0. And we can find cosine of 3 pi equal to -1. And we can find tangent of 3 pi equal to 0 divided by -1, which is 0. Because tangent is just the y coordinate divided by the x coordinate. And sine is the y coordinate, cosine is the x coordinate. 5 pi, same kind of deal. It's actually, that's kind of not a very interesting question because we've already kind of talked about it. But 5 pi is again at the same spot. So you can go around and around and around the circle as many times as you want, and you're still going to end up at somewhere on the unit circle where we can find the x and y coordinate. It doesn't matter if it's 5 pi or if it's 501 pi, right? We just have to find out where we are on the unit circle. Now, the nice thing about multiples of pi is you're either on the right side of the circle or on the left side of the circle. Right, if we think about our unit circle for a second, I'm just drawing again. When I'm drawing a quick unit circle, whoa, wow. Well, first of all, I tried to draw a better circle. Right, I'm really thinking about what's going on at these 4 points. This point having the point 1, 0, 0, 1, -1, 0, and 0, -1, and this angle being 0. This next one being pi over 2. Pi, 3 pi over 2, 2 pi. You could keep going, but you don't have to stop there. You can keep going, revolving around and around the circle. This could be also 5 pi over 2. This could be also 3 pi. This could be also 7 pi over 2. This could also be 4 pi. And we can kind of see that the left and the right side, the left side is always going to be an odd multiple of pi. The right point is always going to be an even multiple of pi. So someone said, what's cosine of 62 pi? We know we're on the right side because 62 pi has to end us up over there. So cosine of 62 pi would be +1 because we know we end up at that point because one revolution is 2 pi, another one's 4 pi, another one's 6 pi, so on and so on and so on and so on and so on. 31 revolutions later, we end up back in the same spot. On the other hand, cosine of 5 pi is on the left side. So cosine of 5 pi is going to be -1. And then tangent to 17 pi over 6. So here's what I see. I see something pi over 6. I see that I didn't leave myself a lot of room here. I see a reference angle of pi over 6. And since I don't really want to draw it again, looking back at pi over 6 for just a second, I see that, well, for pi over 6, the y value is 1/2, the x value is √3/2, so tangent is going to be 1/2 divided by √3/2. I know I'm not even thinking about the actual angle yet. I'm just thinking that tangent of pi over 6 is going to be the y value 1/2 over the x value, which is √3/2, which simplifies to 1 over √3, which rationalizes as √3/3. We're almost there. All we have to do now is figure out what quadrant that angle lives in. Which maybe I may be underselling it. It's not always an easy task to figure out what quadrant that angle is in. That angle is bigger than a whole revolution. 17 pi over 6. If I actually did the division, 17 pi over 6 is going to be 2 pi plus some more. Right? Because 17 pi might, in fact, let's even break it down here. 17 pi over 6 is 12 pi over 6 plus 5 pi over 6. And the reason I broke off at 12 pi was because 12 pi over 6 is 2 pi plus 5 pi over 6. So that's one whole revolution and then another 5 pi over 6. So I'm going to end up back in the second quadrant. Right? One whole revolution. And then 5 pi over 6 is almost pi, but not quite. It's almost getting me to that left endpoint there, but not quite all the way. So if we're in quadrant 2, tangent's going to be negative. The tangent to 17 pi over 6 is going to be negative √3/3. Sorry, I know I got a little messy here. So when we're thinking about evaluating trig functions, at least when I'm thinking about it, I'm really just thinking reference angle, quadrant. Find the value, find the sign, SIGN. Unless it's one of these quadrantal angles, which again, I don't feel like I have as many examples of as I feel like I should. So yeah, let's talk about these things and then we'll come back to that for a second. So tangent theta is sine theta over cosine theta. That is a very, very common trig identity. It's called one of the quotient identities. And we can kind of see that, right? If sine theta equals, right, if tangent theta is equal to y divided by x, well, y is what sine of theta is equal to, and x is what cosine of theta is equal to. So it's not a big stretch there to see that, oh yeah, tangent theta is going to be sine theta over cosine theta. And in a similar way, we can see that cotangent of theta, which is x divided by y, is also equal to cosine theta divided by sine theta. These are very common trig identities that we are aware of. So for a second. And then the other one that comes up kind of a lot is that sine squared of an angle plus cosine squared of the same angle is always equal to 1. No matter what angle in your unit circle you are, whether you're pi over 6 or pi over 2 or pi over 3 or something else, some other pi over 9, right? It could be some bizarre angle, 62.3 degrees. No matter what the angle, sine squared of the angle plus cosine squared of the same angle is always equal to 1. And the way you can see that is if we draw a lot of little unit circles. Take a unit circle and draw the angle theta. Well, if this is x
This is y. This is the point x comma y, which is cosine theta comma sine theta. Pens are not doing their thing. Sorry. Well then, oh, and the hypotenuse is 1. We know from the Pythagorean theorem that x squared plus y squared is equal to 1 squared. But x is our cosine. So we've got cosine squared theta, y is our sine. That's sine squared theta, and that's equal to 1. And that's kind of the nicest way of writing it. I will point out that this is just, oh my gosh, words. An abbreviation for cosine theta quantity squared. And this is just an abbreviation for sine of theta quantity squared. It just gets kind of to be a little bit tedious to write all those parentheses out all the time. So people often will abbreviate sine of theta quantity squared as sine squared theta, and so on. Okay. So let's verify this trig identity, because even though it looks like it should be true, and it is true, it's still good to see that it's true for a particular value. So let's go ahead and plug in 4 pi over 3 and see what we get. So I'm going to find sine squared of 4 pi over 3 plus cosine squared of 4 pi over 3. And I'm not going to say it's equal to 1, even though I know it's going to be eventually. So when you're asked to verify an identity, it's usually good to start with one of the two sides and work on that side until it ends up equaling the other side. Or alternatively, you might work on both sides independently and eventually get to a point where they both equal the same thing. But if I just write it's equal to 1 right now, I'm kind of defeating the purpose because I'm saying it's equal to the thing that I'm trying to show that it's equal to. It's not a huge deal, but it's a big enough deal that I should mention it. So I'm going to rewrite this as sine of 4 pi over 3 quantity squared plus cosine of 4 pi over 3 quantity squared. All right, my reference angle is pi over 3. Sine of pi over 3 is, let's see, it's not the smaller angle in the first quadrant, it's the bigger angle in the first quadrant. So sine is the bigger value, which is the root 3 over 2. I've got extra parentheses here, that's all right. And in the first quadrant, again, I know I'm not actually in the first quadrant, but in the first quadrant, cosine of pi over 3, well, again, pi over 6 is your smaller angle, pi over 4 is your middle angle, pi over 3 is your biggest angle. Cosine is the smaller value because my x values have gotten smaller as I've moved that way in the first quadrant. Cosine of pi over 3 is going to be a 1/2. But then since our angle is actually 4 pi over 3, which is in quadrant 3, both of these are negative. Now, it doesn't really actually matter that they're negative in this particular problem because they're both going to get squared anyway. Negative root 3 over 2 squared is going to be, let's see, the square root of 3 squared is 3, and 2 squared is 4. And the negative thing times the negative thing is a positive thing. Similarly, negative 1/2 squared is going to be a positive 1/4. And 3/4 plus 1/4 is 4/4, which is equal to 1. Check. We showed it. We did the thing. So that's kind of the idea of what it means to verify a trig identity or to prove a trig identity or show a trig identity is actually true, is to do something like this, to start with one side and show that it's equal to the other side. And that's something we do a fair amount of with trigonometry because it's important to be able to simplify trigonometric expressions into something that is easier to deal with. Let's look at a couple more examples. Yeah, and I've got a few more. Yeah, I got time. Okay. Sorry, I'm gonna grab this here. Yeah, we'll come back to that. So let's look at this, simplifying these things to a single trig term, and then we'll roll back around to looking back at the quadrantal angles. So this is kind of in the same vein as verifying a trigonometric identity, but it's got a slightly different flavor, and we're just going to try and take this expression and use some of the identities that we have to simplify it into something that has only one term in this particular problem. So my usual starting place, if I'm trying to simplify a trigonometric expression into one term or simpler terms, is to start by changing things into sines and cosines. That's usually my go-to first step. It's not always my first step, but it's often. I'm going to think of this as cosine of x times, instead of cotangent plus tangent, I'm going to write cotangent of x as cosine of x divided by sine of x. And I'm going to write tangent of x as sine of x divided by cosine of x. And then what will often be an issue when we're trying to do something like this is we're going to have fractions that often need a common denominator before we can add or subtract them together. So I've got cosine over sine plus sine over cosine. I need those to have a common denominator. So I'm going to write this as cosine of x times, I'm going to multiply cosine x over sine x by sine x over sine x. Sorry, by cosine x over cosine x. Apologies. I'm going to multiply the sine x over cosine x by sine x over sine x. So now when I simplify this, I've got cosine of x times cosine is cosine squared over sine times cosine is just sine of x times cosine of x. I can't do anything with that. Plus here I've got sine of x times sine of x, which is sine squared of x, over the same denominator, sine of x times cosine of x. And now that I have a common denominator, I can put those together. So I can write this as cosine of x times cosine squared x plus sine squared x all over sine x times cosine x. Then what? We have a trig identity. Cosine squared x plus sine squared x is equal to 1, no matter what x is. So we're going to take this and rewrite it as cosine of x times 1 over sine of x times cosine of x. And at this point, you can probably just cancel a cosine. You could also, if you prefer, you could take one additional step and write it as cosine of x divided by sine of x times cosine of x. And then we can cancel the cosines. Cosine divided by cosine is 1. I'm going to get 1 over sine of x. And although that probably would be fine to leave it that way, there's a better answer. Instead of writing 1 over sine, I would prefer to write cosecant of x. So again, when I'm trying to simplify a trig expression into a simpler expression, my usual steps are to first, if I don't see anything obvious, write things in terms of sine and cosine. Meaning rewrite tangent as sine over cosine, rewrite cotangent as cosine over sine, rewrite secant as 1 over cosine, and rewrite cosecant as 1 over sine. And then after that, see what you can do. So let's apply that thought process to the next question as well. So this looks gnarly. I got sine of x over secant of x times cosecant of x minus cotangent of x. And I'm going to start off by just rewriting it. Got sine of x on top. I've got secant of x, which is 1 over cosine of x, times cosecant of x, which is 1 over sine of x, minus cotangent of x, which is cosine of x over sine of x. And as will often be the case, I have things that I want to subtract together that don't have a common denominator. So I'm going to give them a common denominator by, let's see, well, this here, 1 over cosine times 1 over sine is just 1 over cosine times sine. But this cosine over sine, I would need a cosine in the denominator to be able to have those fractions having the same denominator. So I'm going to write this as sine of x over 1 over cosine x times sine of x minus cosine x over sine of x times cosine x over cosine x. So then I can put things together. So then I can rewrite this as sine of x over 1 minus cosine squared x all over sine x times cosine x. Now here's where you have maybe choices as far as what you want to do next. One option would be to rewrite 1 minus cosine squared x. In fact, let's go back to the previous page for just this previous page. Sure. Yeah, let's just write this down on a new page. We'll come back to that in a second. So 1 minus cosine squared x, well, you can maybe see there's a trig identity there. 1 minus cosine squared, if we think about the fact that sine squared x plus cosine squared x equals 1, if I subtract cosine squared x from both sides, I've really got sine squared x equal to 1 minus cosine squared x. So I can totally rewrite this as sine of x over sine squared x over sine x times cosine x. And then I can cancel. So this is where I would maybe be a little bit hesitant to start canceling stuff, because I just got lots of fractions and fractions. I'd rather not have fractions and fractions. So I'm going to rewrite this as, instead of sine x divided by this fraction, I'm going to write this as sine of x times the reciprocal of this fraction. Sine x times cosine x over sine squared x. At least to me, that feels a little easier to see how things are going to cancel. I can cancel a sine here with one of the signs there, and I'm left with sine x times cosine x over sine x. I really should just cancel both of them, but I was trying to show the steps here. And then this sine x can definitely cancel with that sine x, and we're left with just cosine of x. Okay, so simplifying these trig expressions down to one simple expression is a process. It can be a little daunting sometimes. It's usually not too terrible. Again, I would think about sines and cosines, usually getting a common denominator. And then there's these trig identities that we're going to use if they show up. So let me just point out that although the usual way of expressing what I like to call everyone's favorite trig identity, because it's the one that comes up the most. So the trig identity, sine squared theta plus cosine squared theta equal to 1, can certainly be rewritten in a couple different ways. You could either subtract cosine squared from both sides and say sine squared theta is equal to 1 minus cosine squared theta. Or you could subtract sine squared from both sides and say that cosine squared theta is equal to 1 minus sine squared theta. There's also a couple other things you can do with this that do come up. Yeah, we should definitely, I should talk about them right now. So another thing you could do is you could take that identity and divide everything, divide each term by, let's do sine squared first. Let's see what we get. I get sine squared theta divided by sine squared theta. I get cosine squared theta divided by sine squared theta. And I get 1 divided by sine squared theta. So sine squared divided by sine squared is what? Right. And what's cosine? What's another name for the trig function where it's cosine theta divided by sine theta? Is that one tangent or cotangent? Cotangent. So, but I don't have just cotangent, I really have cotangent squared because it's cosine squared divided by sine squared. So that's going to be cotangent squared theta. And 1 over sine is cosecant. So 1 over sine squared is cosecant squared theta. This is another trig identity. It comes up less often than this one, but it is an important trig identity. It does come up. And then I want you all to try doing the same thing, but instead of dividing each term by sine squared, take your sine squared theta plus cosine squared theta equal to 1 and divide everything by cosine squared. And then simplify it and see what you get. I'll give you like a minute and a half. I'm going to write it down too. Okay. Oh, I didn't give you all the time I said I was going to give you. It's been like a minute. Listen. So just like cosine over sine was cotangent, sine over cosine is tangent. So sine squared over cosine squared is tangent squared theta. Cosine squared divided by cosine squared is 1. 1 over cosine is secant, so 1 over cosine squared is secant squared theta. Now I'm going to rewrite this in just a slightly different way because it's usually more often expressed as 1 plus tangent squared theta equal to secant squared theta. Or prepare yourself for something you will probably never be able to forget, because I have not been able to since the student said it to me. The way a student told me they remember this trig identity is I tan and get sexy. Can't forget it. It's impossible. Like you're like, oh, it's stuck in your head now forever and ever and ever. So 1 plus tangent squared equals secant squared theta, or I tan and get sexy. When I was teaching this, like with that student, we also tried to come up with one for this. And since we were living in Colorado Springs at the time, that's where I was teaching before, we came up with I sleep on a cot in Colorado Springs, Colorado. Not quite as good, but you know, it works. So yeah, that's what we came up with that one there. But I tend to get sexy. All right, the other thing we should talk about, yeah, we have a few minutes, is we should go back to some trig unit circle examples, because I feel like this section kind of gives short shrift to the following kind of question. So let's say I want to evaluate all 6 trig functions of, say, 3 pi over 2 radians. So let's see, that's on the circle down here. There's 3 pi over 2 radians. We've gone this far. And the point there is 0, -1. Sine and cosine, no big deal. We can do those just fine. I do encourage you to write them in this order because it's going to be an order you see a lot. So cosine of 3 pi over 2 is just the x coordinate. I started with the wrong one though. We usually do sine first for some reason. Sine of 3 pi over 2 is the y coordinate, which is -1. Cosine of 3 pi over 2 is 0. And tangent of 3 pi over 2, I think this is the reason we write them in this order. Tangent of 3 pi over 2 is the y divided by the x, or the sine divided by the cosine. And so you can see, oh, it's going to be, wait a minute, -1 divided by 0 doesn't exist. So what's always going to happen for these quadrantal angles, whether it's 3 pi over 2 down here, or pi over here, or 0, or 2 pi over here, or pi over 2 up here, or any larger multiple of them, you're always going to get some trig functions that don't exist. Specifically, 2 of them are always going to not exist. Sometimes it's going to be tangent and secant. Sometimes it's going to be cotangent and cosecant. But always 2 of them are going to be just does not exist. Let's find the reciprocals. So the reciprocal sign is cosecant. So cosecant of 3 pi over 2 should be 1 over -1, which is -1. And secant of 3 pi over 2 is the reciprocal of cosine. Cosine is 0, so secant is 1 over 0. Oh, that does not exist. So actually, I stopped here and I shouldn't have. I should cross this out and say, oh, tangent of 3 pi over 2 does not exist. Secant of 3 pi over 2 does not exist. Cotangent of 3 pi over 2 does exist, though. Cotangent would be the reciprocal of tangent, or you could think of it as the x over the y coordinate, which in this case is 0 divided by -1. And 0 divided by -1 is just 0. Right? 0 divided by any non-zero number is just 0. So let's do another one, but I want to point out there's always going to be kind of a pattern for these quadrantal angles. If, what do I want to say here? Two of them are always going to be 0. Typically sine or cosine and either cotangent or tangent. Two of them are always going to be undefined. And two of them are always going to be either +1 or -1. Let's look at another example. Same thing. All 6 trig functions for 30 pi radians. Okay, 30 pi. So let me ask all of you, are we at the top, the bottom, the left, or the right? It's like, it's okay. You know. So let's see. So here's 0 radians, pi radians, 2 pi radians, 3 pi radians, 4 pi, 5 pi, 6 pi, 7 pi. You're running about the right endpoint because that's going to be 30 pi radians is exactly 15 full revolutions. Two pi, 4 pi, 6 pi, 8 pi, 15 times. So then we're right there. And then once we know we're right there, the coordinate there is the coordinate 1, 0, meaning the cosine value is 1 and the sine value is 0. So we can say that sine of 30 pi is 0 and cosine of 30 pi is +1. And tangent of 30 pi is 0 divided by 1, which is 0. I should probably write that out. I would write out 0 divided by 1 equals 0. So fun fact, if one of the trig functions is equal to 0, its reciprocal should be undefined, right? If sine of 30 pi is equal to 0, then cosecant of 30 pi is going to be 1 over 0, which is going to be undefined. Secant of 30 pi, secant is the reciprocal of cosine, that's going to be 1 divided by 1, which is just 1. And cotangent of 30 pi, well, it's going to be the reciprocal of 0. It's going to be 1 over 0, which is going to be a does not exist. You could, if you don't write D and E, you could also write, or you could write the words is undefined. So whenever you're finding all 6 trigonometric functions of any of these quadrantal angles, you're always going to get 2 of them equal to 1 or -1, 2 of them equal to 0, and 2 of them being undefined. It's nice to be aware of that pattern so you kind of know what to expect. So same thing would be true. You also try on your own, finding all 6 trig functions of 5 pi over 2. And I know we're out of time, but let me just ask you all. Oops, sorry, I can't see that. Where on the unit circle, show me by pointing in the right direction, is 5 pi over 2 up, down, left, or right? Okay. So let's think about this here for a second, just because I do want you all to know this. So if I start here at 0, and then that's going to be 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, which is 2 pi, 5 pi over 2. So 5 pi over 2 is actually back up at the top. So one way you could think about that, if you don't like kind of doing what I just did, is you could take your 5 pi over 2 and just start subtracting off multiples of 2 pi. because 2 pi is 1 for evolution. So I subtract off of 2 pi, that's 5 pi over 2 minus 4 pi over 2, which is 1 pi over 2, which gets me back to there. So 5 pi over 2 and 1 pi over 2 end at the same spot, or they're coterminal. All right, that's all the time I have today. So on Wednesday, again, I will be here having class, but if you are not here and want to come virtually or want to watch the video later, I totally understand. I get it. It's the day before Thanksgiving. People will travel. So feel free to attend in whatever way works best for you. I will still be here in person if you want to be here in person. If I don't see you all on Wednesday, have a lovely Thanksgiving. If I do see you all on Wednesday, also have a lovely Thanksgiving. Either way, have a lovely Thanksgiving. And don't forget, tanning is sexy. I don't really tan, like I don't tan. There's another trig identity later on we learn. It's kind of the opposite of that, where it's like 1 minus tangent squared equals something. And I'm like, oh, I don't tan. So that's yes, that's my favorite. I don't tan, I burn. I stay out of the sun. Good. And I'll be over and drop in, or not drop in, sorry, C class right now, and then drop in later at 3. Okay, so it's not that bad. I just always feel like it's just mildly inappropriate.